So we're going to start by talking about complex eigenvalues, because you can have a matrix where all the numbers involved are real. So the kind of numbers that we grew up with. And even though all the numbers are real, we could have complex eigenvalues. We see this because we know we have polynomials where we get complex numbers coming out as roots of polynomials. And we want to talk about, well, how do we handle this? Now, the key thing here is that when we're in this situation, the eigenvalues come in what we call conjugate pairs. So what does conjugate mean? Conjugate means you flip the sign. So if I have a plus bi, what's the conjugate of that? A minus bi. So just whatever's in front of the part with the imaginary thing, the I, change the sign to plus to minus or minus to plus. That's what we mean when we say the conjugate pair. Now, the really cool thing is when we're talking about matrices, we have eigenvalues come in conjugate pairs, but also the eigenvectors come in conjugate pairs. All right. So we're going to start with an example. Verify that 1 plus 2i is an eigenvalue of this matrix, 7, 4, minus 10, minus 5, with an eigenvector of 2, negative 3 plus I. That's the first part. Second part, also give the other eigenvalue and eigenvector. Now you might say, the other one, well, we're saying this is 1. How many eigenvalues should this matrix have? 2. How do we know it should have 2 eigenvalues? 2 by 2. So the size gives you the number of eigenvalues. All right, now you look at this and you might have two reactions. Either like, oh, this is going to take forever and there's not a lot of space. We're going to have to find the characteristic polynomial and take the roots and then do the stuff for eigenvectors. And like, do we really have time for that? No? Someone said? But notice, it doesn't say find it. It says verify it. So verifying should be much simpler. So when I want to verify an eigenvalue, eigenvector, what's my equation I go back to? So the pieces are, I have a matrix, we'll call it A. I have a vector, let's call it V. I have this eigenvalue, let's call it lambda. So what is our basic equation that involves these three objects? A times V equals lambda times V. So if I want to verify something is an eigenvalue and an eigenvector, I don't have to find it from scratch. I say, look, I have my candidate, I just have to check that the equation holds. So we need to check what is A times V, and we need to check what is lambda times V, and then we compare our answers. Which one do you want to do first? A times V? All right. We'll start with A times V. All right, so A times V. Well, that's 7, 4, minus 10, minus 5, the A, and then the V, 2, minus 3 plus I. Okay, so we're multiplying this out. 7 times 2, 14. 4 times negative 3 plus I. Yeah, so you just multiply the whole thing, right? So negative 12 plus 4i. All right, next row. 2 times negative 10. Negative 20. Negative 5 times negative 3 plus I. So minus 15. Oh, sorry, plus 15. Yeah, negative 5 times negative 3 is plus 15. And minus 5i. Okay, well, that's not so bad. 14 plus negative 12. 2 plus 4i. Minus 20 plus 15. Minus 5. Minus 5i. All right. Now, when you look at this, you might say, wait a second, I don't see like a common term to pull out of here. But complex numbers can be a little bit complex in that way. And so that's okay, because we don't actually have to think about pulling something out. We say, all right, we know what A times V is. The next thing is, what's lambda times V? So let's do that computation. So lambda should be 1 plus 2i. And then V, that's plus 2, minus 3 plus I. All right, so this lambda, it's acting like a scalar, which means you multiply both entries by that quantity. So we have 1 plus 2i times that by 2, and 1 plus 2i, negative 3 plus I. Well, the first one I don't think is too bad. 1 plus 2i times 2? 2 plus 4i. Yeah, that's not so bad. You just multiply through by 2. Now the next entry, well, maybe we should think a little bit about here. What do we need to do here to multiply out? We can FOIL. So we're going to expand, multiply in all combinations. But let's do it sort of in 2 steps and say, let's do what would be real, and let's do what would be imaginary. 1 times minus 3, that's pretty real. What's that? Minus 3. That's our first. Now to 2i times I becomes negative 2, because I squared is minus 1. So we have minus 3, minus 2, which combines minus 5. Now we have the other parts. The outer parts are 1 times I, and 2i times minus 3, minus 6i, I minus 6i, minus 5i. And now we say, all right, we've computed A times V, we've computed lambda times V, and now we ask the question, are those the same? Yeah, they're the same. They match, and therefore it is a success. Woohoo! Good. All right. So now that's the verification. We verified it's an eigenvalue for that eigenvector. Are we done with the problem? No? Well, we're out of space, so hopefully the rest of it's not too hard. You have to get the other eigenvalue and another eigenvector. So let's see. We'll try to squeeze it into this little space down here in the corner. So I'll abbreviate eigenvalue as E value. So we know that 1 plus 2i is an eigenvalue. What's the other one? Yeah, remember, they come in pairs. They come in pairs. Okay, the eigenvector, abbreviate that as E vector. What will that be? So again, we say, hey, everything comes in pairs. So this eigenvector goes with that eigenvalue, but the conjugate of this goes with the conjugate of that. So what's the conjugate going to be? Yeah. So the upstairs, what happens to 2? What's the conjugate of 2? The conjugate of 2 is 2, because there's no imaginary part attached to it. So when we take a conjugate of a number with no imaginary part, it's just a number. Conjugate of minus 3 plus I? Minus 3 minus I. All right. And now we are done with the problem. Good. So, sorry, what? Well, we have verified, because we have, someone saying, don't we need to verify? We have, because A times V equals lambda times V. As long as you can show that A times V equals lambda times V, that's a verification. Now, we don't have to verify this, because it didn't tell us to verify. We could, or you can just believe what we say here. But I think this is a let's believe it today. All right. So why do we care about that? Well, we talked about saying, if I have this x prime equals ax system last time, there's this process. We find the eigenvalues. We take e to the eigenvalue t times some appropriate vector, that's the eigenvector, and then we take combinations of those. Now, it's still true if we have complex eigenvalues it still works. It's a completely valid thing, but it doesn't feel right to us in some sense. We're like, even if we have complex eigenvalues, our functions should somehow be real. We want to keep things real. So how do we transform? Now, we've done this before. We had complex roots before, and we said, by appropriately rewriting things, I can take a complex root and turn that into things involving sines and cosines. So we're going to do that again. So here we go. So we have our system, x prime equals ax. All the entries of A are real. Now, the reason that we specify that is to say everything comes in conjugate pairs. All right. Well, alpha plus I beta is an eigenvalue. So we have a complex eigenvalue. A plus IB, an eigenvector. Now, you might notice here that the A and the B are bold. These are bold A and bold B, which means it's just the vector A and the vector B. Now, what that is saying is you take your eigenvector and you pull it apart. And you say, I want to look at the part with the real pieces and the part with the imaginary pieces. As an example, here's this eigenvector over here. And we could say, well, let's write it as the real piece plus I, the imaginary piece. What would be the real part? What's the vector there? 2, negative 3. Right? Because that's the real part, that's the real part. What's this vector? 0, 1. So if I have an eigenvector, or really any vector at all with complex entries, I can always pull that vector into two parts and say, well, the real part of it, the imaginary part of it. So that's what we're calling A plus IB. All right, so here we go. We consider the e to the alpha plus IB times, so alpha plus I beta t times A plus IB. Now, in terms of what we talked about last time, this function is a solution to x prime equals ax. Our goal is just to talk about rewriting it. And now we say, hey, we've dealt with something similar before. Namely, we've dealt with this e to the alpha plus I beta t. And we said that's the same as e to the alpha t cosine beta t plus I e to the alpha t sine beta t. So that was using a really cool fact that if you have e to the I theta, you get cosine theta plus I sine theta. So this is the same thing that we did before. The new part is you have this other thing on the end, A plus IB. Well, we have something times something. What should we do here? We should FOIL, right? Here's something plus something times something plus something. We'll FOIL. And what we'll do is we'll group. We'll say what parts are just real, what parts are imaginary. So if we're grabbing the real parts, well, we can take the first terms. So that would be e to the alpha t cosine beta t times a. So that's the first part. That's real. What else would be real? The last two. Because here you'll get an I squared. I squared becomes a minus e to the alpha t sine beta t times b. So we have the real part. Okay. Well, we've used the f and the l. What's left? Outer and inner. Oi. No, the oi and FOIL. Okay. So the outer parts, that's e to the alpha t cosine beta t times b. And I'm just grabbing what would be attached to the I. So e to the alpha t cosine beta t times b. And the inner, e to the alpha t sine beta t times a. All right, so there's the real part, there's the imaginary part if you were to expand into group. And now the punchline says, hey, remember this is just one solution. There's a second solution out there. What's the second solution that's out there? Conjugate one, right. So the solutions come in pairs. And now you say, because I have these two solutions, by working with both of the alpha plus I beta and alpha minus I beta, if we combine those solutions, we see that both of these are themselves solutions. So this is how we go from complex eigenvalues to real functions as solutions. So these are our answers. All right, great. It's a little bit more interesting than what we had before because we also had the eigenvector floating around, but the idea is beautiful. Okay, good. Well, any questions on this part? Well, let's try this. So, here we go. Solve x prime equals this vector, 7, 4, minus 10, minus 5x, with an initial condition, x is 0 equals 10 minus 8. And look at all this beautiful space here that we get to work with. So much space. So much space. All right. Good. Well, what should we do? Well, okay. Some people are saying, let's start from scratch. All right. But wait a second. This looks familiar. Have we seen something like this before? That's the matrix we talked about before. What? Now, what do we know about this matrix? We know the eigenvalue. In fact, we know both eigenvalues, and we know eigenvector. So we don't have to start from scratch, so that's good news for us. Okay, so we have our eigenvalue, and that'll be 1 plus 2i, and our eigenvector. And that is our, and I'm going to write it in the form where we split it. So 2 minus 3 plus I 0, 1. Okay. Well, that'll save us some time. But we can even say, look, because we have our nice complex roots, we know how to write our answers. That's what this information here tells us. And we know the pieces. We know A, we know B. That's A, B. We even know alpha and beta. So alpha is the 1, and beta is the 2. So what I'm going to do here is I'm just going to copy this down. And so we could say one solution, I'll call it x1, is of the form e to the alpha t cosine beta t times a minus e to the alpha t sine of beta t times b. And then another solution, let's call it x2, e to the alpha t cosine beta t times b plus e to the alpha t sine of beta t times a. So what I've done is I've copied. Because if I have complex roots, complex eigenvalues, I know how to create my functions. So this is going to save us a lot of work. A lot of work. Cool. Well, what should we do next? Plug in. All right. Sounds good to me. Well, what does this become? E to the t cosine 2t times 2 minus 3 minus e to the t sine of 2t times 0, 1. Down here, e to the t cosine 2t times 0, 1 plus e to the t sine 2t times 2 minus 3. All right, so given that I know the alpha, beta, A, B, substitute it. All right. Hanging in there? Okay. Good. Well, we have x1. We have x2. Are we done? No? Yes? Well, maybe we're not fully done. What do we need? I mean, we have two solutions. How many solutions should we have? Two. So we have all our solutions in some sense. Now this is two solutions. What's our general solution look like? Well, we add them together, but not just add them together. What do we do with them? We have some coefficients. So our general solution, well, it looks like some constant x1 plus some constant x2. Here are x1 and x2. So I won't rewrite it all right now, but that's what we'd have. So we have our general solution now. Other than writing a lot of stuff down, are we done? No. What's left? Yeah, this is an initial condition problem. All right, just when you think it's done, it pulls you back in. Okay, so we got to do the initial condition. So what should we do? Plug in. So x at time 0. Well, what is that? 10, negative 8 is equal to some constant c1. Well, plug 0 into x1, and what will you have? So the nice thing about sine of 0 is it's 0. Cosine of 0 is 1. E to the 0 is 1. So we're left with 2, negative 3. Plus some constant c2. Okay, now plug 0 into x2. 0, 1, because the sine part will make the second piece go away, and then you have 1 times this vector 0, 1. Okay, or if you look at the first row says 10 is 2c1, and the second row, negative 8, is minus 3c1 plus c2. I think we can probably solve. We don't have to go through and do some augmented matrix. I think we can do this one. What about C1? 5. Almost no hesitation there. Now, since we know C1, this minus 3C1, we can cross it out and replace it by minus 15. So what does that tell us about C2? 7, because you can add 15 to both sides. Wow, this is cool. Okay, so we now know that C1 is 5, and we know that C2 is 7. So we can put it all together. So our final answer, x, is 5 times x1. So that's e to the t cosine 2t, 2 minus 3, minus e to the t sine of 2t, 0, 1. Okay, so 5x1 plus 7, c2, that's our c2, times x2. All right, e to the t cosine 2t, 0, 1, plus e to the t sine of 2t times 2, negative 3. Done. Done. There's a question.
Where do the conjugates come in with this? Do they have to do the same thing?
So what happens, so this goes back, so the question is, where do the conjugates come into play? And the answer is the conjugates are in play once you write things in this format. So if I only have alpha plus I beta, I can't get this as a solution. This is only a solution when I combine alpha plus I beta and alpha minus I beta. So the conjugate came into play in that we are saying both the eigenvalue and its conjugate contribute to this solution, and both the eigenvalue and its conjugate contribute to that solution. So that's where the conjugates are coming into play. It's not that we're ignoring it, it's just that they've combined together. Their powers combined. They are our two solutions. All right. It's nice to be able to do a problem and not have to take half of class. You know, I miss those days. They were good days. All right. So now we're going to jump into a different topic. And there's a lot of text here, but the thing is, it's about pictures, so we should really jump into pictures. And we're going to talk about visualization. How do we think about these pictures? I know what's going on here. Now, we've talked about visualization before in our class, where we talked about slope fields. So that was a very early example where we had y prime equals f of xy. And what we did is we said, okay, you can imagine we draw our plane, xy, and at every single point, we drew a tiny line. Now, what that line was, it was the behavior of the function nearby. It was really just mini tangent lines. Because at every point, we knew the slope. And so we said, okay, here's what's happening. We have the slope of the function nearby. And then we would say, well, if we have that, we can somehow follow the slopes and get an idea of what the function is doing, or the solution is doing. So that these slope fields gave us a visualization of what solutions look like. We want to now talk about something similar in our new setting. So we're going to think about our setting as x prime equals ax. And here we get into some interesting ambiguity, and we're going to try to use it. It's a little bit dangerous, because whenever you say ambiguity, it can be a little bit ambiguous. But our ambiguity comes from saying, how do we think of this, x1, x2? If you don't want to think about it generically, think about it as like 1, 2. How do we think of that? And there's actually two different ways we can think about it. And if we think about them both simultaneously, then what we're about to draw will make sense. One way to think about it is to say, oh, I can think about it in terms of location. Because I'm saying, oh, I should be at x1 is 1 and x2 is 2. So I can think about it as being a particular spot to work on. So that's one interpretation. So I can think of it as a point. But the other interpretation is I can think of it in terms of what we call a vector. And we've been using this phrase a lot. Now, vectors are really important ideas. You'll see this in physics. You'll see this a lot if you take, for example, Calculus 3. What are vectors? Well, the way I like to think about a vector is it's talking about change, how something is changing. And so we can think about, all right, I can measure change by picture-wise as like an arrow. So from my spot, which way should I be going? So the arrow points in the direction I should go. And the other thing is I should have the length of the arrow. A very big arrow says a big change. A very small arrow says a very small change. But how does that relate to what we're doing? Well, we can also describe it as a change in each direction. And so the other way to think about this notation here, this 1, 2, is that this is a vector, and vectors inherently are telling us how we're changing. So what that would tell us, and it doesn't have to be at this point, it can be at any point we want, is I would come to a particular point and it says you should go over 1, change 1 in the x1 direction, change 2 in the x2 direction. So that is a change. So I can think of it as a vector x1, x2. So how does this all fit together to make direction fields? Well, we plug a point in, and we have this a times x. So we have x as a point, we plug it in, and now that says at the point x, we plug in, we get a value, and the value that comes out is a vector. And that's done as how we should change. So now what we do is we go through. And at every point, we plug the point in, out comes a vector. So we draw an arrow. Now to help us keep our picture somewhat contained, we're going to scale all the arrows to be the same length. You should really have the arrows be different lengths, because a long arrow should say, oh, you're going very quickly here. A short arrow says, go very slowly. But we'll make them all the same length. But now you just repeat. And you do this. And you can imagine this process, if you were a person, it might take a little bit of time. But who likes to do computations? Computers. Exactly. So a computer would go through and make lots and lots of little arrows. So at every single point, the arrow is an indicator of saying which direction should you be going from that point. Now, another comment we should throw in, why do we have arrows here but not there? So when we did slope fields, we never put arrows on there. What's the difference?
There were tangent lines.
Well, tangent lines, right? But how do we know which way to go? Well, we know which way to go because we had this sort of input. There's this natural input that goes in there, and we said, oh, we should always be going from left to right. So there's a built-in direction. But now, notice when we talk about functions here, we don't think of x2 as a function of x1. We don't think of x1 as a function of x2. Our input is t. It's time. And so because of that, we don't have a natural direction that we always go. So sometimes we might have arrows pointing to the right. Sometimes it might be to the left. It just depends on what's happening at that particular point. All right. But once we have our arrows, we just do what we did before. Follow the arrows. And that tells us what solutions will look like. It's the same philosophy. Now we just have to add in the directions. Okay. One other comment to make. And that deals with eigenvectors. And we've talked a lot about eigenvectors. And this is our chance to say, hey, eigenvectors, they're really cool for a very good reason. So when we think about eigenvectors in relationship to our direction fields, so we'll have here, we'll have our x1, here's our x2, and now let's suppose that this is the direction of an eigenvector. And some direction. Now remember, we can always scale, so it's the eigenvector points in that direction. Well, if we're in the direction of an eigenvector, remember, for eigenvectors, we have that ax equals lambda x. So, I have a point here. We'll call it x. Because it's in the direction of an eigenvector, this vector, if I think of it instead of a point, but I think of it as going from the origin to there, that is an eigenvector. Now, the punchline. Suppose lambda is positive, and I plug in ax equals lambda x. Where does my arrow point? That should go from this point. Which way?
Up to the corner.
It will follow the same direction. So if I'm in the direction of an eigenvector, my arrows say, hey, that's a great direction. I like that direction. Keep going in that direction. So this is when lambda is positive. We move away. In fact, we're going to move away from the origin. We move out. What would happen if lambda had been negative? Now where would we point?
The origin.
We point in the opposite direction because the negative sign says point the other way. So if lambda is negative, we're going to point towards the origin. So we're going to actually move to the origin. So lambda positive, move away in that same direction. Lambda negative, move towards. We head towards the origin. Now what's the last case? 0. So if lambda is 0, where do we point? Nowhere. Why? Well, what's our vector? The 0 vector. So when lambda equals 0, what do? Well, the 0 vector says, don't do anything. Stay put. Don't change. I like to think of it as sort of the art history major of vectors. Stay where you are. You don't need to change. You're great. So lambda equals 0, stay put. Don't move. So in particular, if we have a 0 eigenvalue, there's some direction associated with that where you never move. Everything's stationary. All right, great. Well, so now we're ready to actually see some pictures. And let's go through and take a look at a bunch of possibilities here. So we're going to do our picture day. So our first one. Let's suppose both of our eigenvalues are positive. And we can assume that they're different. So what we'll see, the first point will always be an example. So this is x prime equals, in this case, 10 minus 6 minus 211. So all these will be a matrix times x. And down here will be our direction field. So the direction field will always correspond to that matrix. The second line here says, look, you've got some eigenvalue and eigenvector pair. So eigenvalue 14 points in 3, negative 2. Well, 3, negative 2 says go over 3, and then we go over 3, that's positive 3, down 2. So this part right here, this is the 3 minus 2 direction. Other eigenvalue is 7, and that'll point in 2, 1. And so that's over 2, up 1, over 2, up 1. So this is the 2, 1 direction. And we see that both of the eigenvalues are positive. And you can also see, if you look at it, it's like, oh, we really are moving straight along in those out from the origin. And now we say, okay, well, great. What happens if you're not on that? So in other words, you're not right on some multiple of an eigenvector. What can we do? Well, so suppose we start here. What should we do? Well, we should follow the arrows, right? The arrows tell us where to go. So it's telling us to go, and it looks like, if we follow the arrows, we're going to be turning. So which way are we turning to? I mean, which one are we biased towards? Are we biased towards our direction 2, 1, or to our direction 3 minus 2? 3 minus 2. Why should we be biased towards that? Well, look at the eigenvalues. Which one has the larger eigenvalue? The 3 minus 2 has a larger eigenvalue, which means that this is really, should be, for lack of a better phrase, blowing up faster. Where we think blowing up, it gets bigger a lot faster in this direction. So that in the 3 minus 2 direction, there's a bigger pull. So if I have a solution, it's going to be pulled more in that direction than in this direction. So that's why you'll see a bias. And you can go through and do this for all the points here. So, and well, you do as many as you feel comfortable doing. So this is one of those sort of like choose your own adventure type things. Here we have a word. The origin is a source. What does that mean? Well, so there's a formal definition. I think the book likes to say if you think about where does everything come from? So if you ran time backwards, where do you all head towards? The origin. So in some sense, the origin is the source of all the different curves if you ran time backwards. So you should think of this, though, as saying the origin is the source, saying everything goes out from the origin. So everything's moving away from the origin. That's what we mean when we say a source. Now, I didn't say this before, so I should just go ahead and add a quick note here. We'll add it to this part right here. If I have x prime equals ax, what happens at the origin? So if I'm at this 0, 0, what can we say about x prime? It's 0, 0 again. So if I'm at the origin, where do I stay? I always stay at the origin. So the origin will always be a point where you never move. So you always will stay at the origin, regardless of what's going on with the rest of your eigenvalues. All right. So that's our first example, but we have more. Okay, next one. Suppose both our eigenvalues are negative. All right. We actually have the same directions. The only thing we've done is we've changed the signs. And say, okay, all right. So along the direction of our eigenvectors, we now flow in. All right. Great. And you can even pick other points and follow the curves in. And you get all sorts of fun, interesting behaviors. Now, if you look at these two pictures, what do you notice about them? They're very similar, right? What's the difference? So there's a visual difference, and then up here there's a difference that we have there. So the visual difference is in terms of the arrows. What have you done to the arrows? You've flipped them around. You have them pointing in opposite directions. What have you done to the matrix? You've negated it. Put a minus sign in front of it. All right. Now, what you've done, there's a fancy way you can describe this, and we can call this a time reversal. In other words, make time go in the opposite direction. And you might say, well, wait, how does that work? Well, suppose I look at our equation x prime equals ax. And consider our new function, we'll call it y equals x of minus t. So the only thing that y does is it has time go opposite to what we expect. So that's what we mean by reversal. Time flows in the opposite direction. Well, what can we say about y prime? Think chain rule. That'd be negative x prime, which would be negative ax, because x prime equals ax. And now, that makes it negative ay. So that's why you get this reversal. So you can always say, hey, if I want everything to change directions, change your matrix to the negation of it. All right, one other thing to point out here. We talked about the origin being the source here. That says everything flows away from the origin. Here, it's a sink. Well, what's happening in this case? Everything goes towards the origin. So that's the sink. Everything moves towards the origin. All right. Well, both positive, both negative. What's the next thing we can look at? Yeah, half and half. So one positive, one negative. So this is an example. And we see in one direction, we have a negative eigenvalue. In particular, it's this direction. We can tell it's a negative eigenvalue because we're flowing towards the origin. So negative eigenvalues we should be flowing towards. In the other direction, which is this way, we're going away. That's our positive eigenvalue. And if we pick any other point, we again can follow the arrows around. And we see that we will sort of, even if we start near the part going in, eventually we'll pull and follow the part going out. So we have some really fun curves. All right. And we call this a saddle. Oftentimes, when we think of saddle, for example, if you've done Calc 3, in Calc 3, we say, well, a saddle, in one direction, it looks like we have one type of behavior, like it's a min. In another direction, we have a max. If you think about the picture we often draw for saddles, it's this little picture here. It's sort of, the idea is saying, hey, in one direction, it has one type of behavior, and in the other direction, it has the opposite type of behavior. And that's really what's going on here. In some direction, we go out, and in some direction, we go in. So whenever you have that saddle, it's sort of a combination of behaviors. All right, well, other possibilities. We could have a 0 eigenvalue, and then maybe the other one's positive. Well, it's easy to spot the 0 eigenvalue. In this picture, it's along here. And what's happening on this line if it's a 0 eigenvalue? Well, the arrows are slightly off the line. On the line, what's happening to the points on the line? We're stationary. We stay put. If we go off the line ever so slightly, so like here, we're on the line, we stay put. We move just a little bit off, then what happens? Then we start to move away. Now notice, what do these solutions all look like? Yeah, they're all straight lines. And they're all straight lines in the direction of the other eigenvector. And so if we have one eigenvalue of 0, well, then all our solutions, they all move in parallel lines. Now this has moving away from this particular line. If I wanted to move towards, what could I do? So if I wanted to flip the arrows, how do I do it? Put a negative. Put a negative changes the arrows. All right, a few more. We could have two eigenvectors which are the same, two eigenvalues are the same, but we come up short in the eigenvectors. So in other words, there's only a single eigenvector. There's not two of them. So here's an example where we have a single eigenvector for the eigenvalue 7. So along there, we move out. But if we're not on that, we have some other strange things happening. You can see that there's this, almost like this twisting going on that's pulling us away somehow. And what's going on? Well, that's a great question, and we're going to talk about that in a future class. A couple more, really quickly. Just give me about another minute here. Pure imaginary. If we have pure imaginary roots, what should our solution look like? It should look like, well, in terms of the function, sines and cosines. Sines and cosines mean that we're periodic. We repeat. So we have to come back. So that means if you follow around, what you'll eventually do is you will come back to where you started. So everything looks like an ellipse. Now that's if you're a pure imaginary. Well, you don't have to be pure imaginary. You could have a positive real part. If you have a positive real part, that means you have something that looks like e to the at. As time goes forward, what happens to e to the at? It gets big. And so what's going to happen is that you're going to move out so that you have spirals that move away from the origin. So in this case, the origin is a source and you move out. Well, what would happen if your real part was negative? Then that e to the at gets small, which means that as time moves forward, you're going to spiral in. So you move in towards the origin. So there are some examples of things that you might see. And that's it for our picture day. We'll continue again next time. Have a good day.